So suppose you are given a function f of x, okay, and the inverse of that function exists. Yeah. So let's write it like this: y is f of x. Okay. So the function I am going to denote, the values of it denote by y. Okay. Then what is x? F inverse y. When I invert it, it will be f inverse y. Now theorem says this: if you take the derivative of f of x, okay, times the derivative of f inverse. See, f inverse is a function of y, correct? So when I have to take a derivative of this, I should take the derivative with respect to y. And here f is a function of x, I take a derivative with respect to x. Multiply the two, this is 1. I will write it in another form. So instead of writing this way, we can also write, instead of fx, let's put just y, so it becomes dy over dx. Okay, I have not introduced really this notation, but I believe you have already seen it and you know it, okay? No, I don't think so. Okay, I've just written, I didn't tell you why. Okay, but anyway, that's dy over dx times, or maybe at a later stage I can tell, f inverse y is what? X. So it is dx over dy is equal to 1. See, here it is very easy to remember if you write it this way. It looks like as if dx have cancelled and dy have cancelled. Okay? But one has to be careful in thinking of these as ratios or something. That has no meaning actually. You cannot think of dy as something on its own and dx as something on its own and then divide. That's a meaningless thing. So I prefer writing it this way for clarity. But this is very suggestive notation, okay? So notation by Leibniz, so you can remember it this way also. Is this statement clear? Okay, good. So this theorem, make sure you remember it. It will be very useful. Let's take some examples of this. So let's take the function y equal to x square. Okay? Or maybe I'll be a little bit more elaborate. Okay. Y is y of x, it's a function of x, is this function f of x, which is x square. Okay. So what is f inverse of x? Sorry, not f inverse. F inverse of y. So f inverse of y what is the inverse of x square?
Why will it be f inverse of y instead of f inverse of x?
Take that relation. Take the inverse both sides. F inverse of y is equal to x. Is it not clear?
Yes.
See here, x, y, right? Whatever curve you have, given a value of x, that's the value of y. But now we are asking, given the value of y, what's the value of x? So that is why your inverse function is a function of y. Okay? Okay. F inverse of y is?
2x.
Yeah, square root of. Is that all? No, there are two possibilities. So you are solving this, right? Y equal to x square. You are solving it, right? So x plus minus root y. That's y equal to x square. given a y, I am asking this value of x. But there are two values. Given this y, this minus x also is a solution. That's why plus minus y, plus minus root y. Okay? Okay. Now we will just try to use that theorem. But before that, I have to ensure that the inverse function is defined. This is not a function, right? For a given value of y, you have two values. That's not a function. A function has only one value for a given value of its argument. So for a given value of y, I should have only one answer, not 10 answers or 2 answers. So I will choose one of these. Correct? Here, if I restrict this to x greater than 0, then I'm only here, okay, only in this part. And when I then look at the inverse corresponding to this, there is only a unique answer because this is not part of it. Okay, so if I restrict the value of x for the function, the inverse function gets well defined. Is that fine? Is that fine? Okay, so that's why I put this qualification x greater than 0, and we will see that later in other examples also, that to make inverse a single valued function, I might have to put certain such restrictions. So if that is the case, then my f inverse, so if I take y equal to x square with x greater than 0, then f inverse of y okay, and
plus root y.
sorry, plus root y. And what is f inverse y? That is x. Correct? F inverse of y is x. Okay, now let's use the theorem. What's dy over dx and what's dx over dy? Okay. This we will verify that it comes out to be 1. Okay, so we are just checking whether my claim is correct, at least in this case. So what is dy over dx? The derivative dy over dx is 2x times. What is dx over dy? What's the derivative of x? Dx over dy, because x is square root of y. Okay, let me do it just in 2 steps.
Y over 2 root y.
So what is x? X is square root of y. Okay? This is 2x times 1 over 2 square root of y. You remember? Derivative of square root of x is 1 over 2 square root of x. Or derivative of square root of y is 1 over 2 square root of y. But what is square root of y?
X.
Square root of y is,
X.
see here, square root of y is x. So that is 1 over 2x. Okay, good. Okay, and these two cancel and give you 1. So at least this theorem has been checked for this example. Okay, I'll give you another example. So remember, here the issue was the function y equal to x squared for a given value of y had two solutions. Okay, and I restricted the values of x to be greater than 0 so that when I choose a value of y, I have only one possibility, not this one. Okay, and then I proceeded. Let's take another example. So this time I'll take y is equal to x cube. And so x, how do you get x? You take the cube root of y. That's the inverse function, you agree? Let me write it in 2 steps. So I will write it again as y is equal to f of x is equal to x cube. That is what I have chosen the function to be. Okay. So f of x, the values I am calling y. So x, which is f inverse of y, how do you get x out of it? by taking f inverse. So f inverse of y, what was it? What is that? It is 1 x y power 1 over 3. Is that fine? You agreed? Okay, let's see whether we have problem like previous time, where I had to restrict the value of x to be positive. Remember this? So let's look at the graph of it. Can you draw the graph of it? Good, that's correct. So the graph looks like this. Slope here is 0. Okay? Now see, for a given value of x, you can find the value of y. Okay? But now, for a given value of y, I have only this value of x. There are no 2 possibilities or 3 possibilities. For a given value of y, let's say take this one, I'm here, that's the value of x. So this time I don't have that problem. Okay? So clearly inverse exists. And you know what the inverse function looks like. It is just take this one and rotate that way. Okay? What looks like a 0, the slope is 0 here, will become what? It becomes infinity there. So you have a problem not with the value of the function, but the derivative of the function. Right? Because the inverse will look like this. Inverse will look like, so this,
Like this.
correct. Just hold on. I'm trying to reflect it in the mirror. Okay, I'm putting it in the mirror. It will go like this. Correct? Yeah. Is it not correct? I think that is.
Yes, it's correct.
I mean, it's not a mirror image of that one. That might be confusing. But the shape should be correct, right?
Will it be like this?
Let's see.
Or like this? It should be like this.
Right. It should be like this.
That's what I was thinking.
No, see, this is correct. It's the same thing drawn here, right? So if I take y here and x here,
No, yes, that's
see, it's the same thing, right? It's not that we have a different graph. Same graph. Just take y-axis here, x-axis here. But it's the same plot. So look, as you go towards positive x, you are steeply increasing in the positive y direction. If you are going towards positive x, you are steeply increasing in the y direction. It's the same plot, right?
I can also take this as my axis.
Okay? So for a given value of y, I have a unique value of x. So you see, that is what I said. The derivative here, it doesn't look like that here, but the derivative here is infinity, right? The slope is really vertical here. Okay? Anyway, so other than x equal to 0, it's fine everywhere. There is no problem. So let's find out let's verify the theorem. So let's see whether dy over dx times dx over dy turns out to be 1. So what is dy over dx? What's the derivative of x cube? 3x square times. What's the derivative of y to the 1/3? It's, so derivative of y to the alpha d over dy is alpha times y to the alpha minus 1, correct? So alpha is 1/3 now, so you get 1 over 3 times y to the 1/3 minus 1. That 3 cancels. Okay, let's keep it. 1 over 3. Okay, this might be confusing. क्या था यहाँ? So this is what? Y to the 1 over y to the 2/3, I guess. Yeah. So this is minus 2 over 3, y to the minus 2 over 3, but that is 1 over y to the 2 over 3. This is 3x square times 1/3 of y power 1 over 3 square, right? Because that is what is. Now what is y over 1 over 3? Y 1/3 is x. So that's x. That's x square. That x square here, 3 here. So 3x square, and also in the denominator 3x square. So that cancels. Proof. Okay? So verified. So this works. And you also understand how to use it. So till now, I have been just showing or verifying the theorem. But that's, there is, what's the point of having a theorem which you can just verify things that you already knew. So I am going to now use it to find out the derivative of inverse trigonometric functions. Okay?